Hello, we are going to continue with chapter 7 in this video. I'm going to cover sections 3 and 4, and really what that means is we're going to cover a reaction called SN2. In an SN2 reaction, we are completing a substitution reaction. So let's first just talk about the name. So here's our SN2. The S stands for substitution, the N stands for nucleophilic, and the 2 is telling us that it's a bimolecular reaction, which means that there's 2 molecules or 2 reagents reacting at the same time. Here's our reaction. We're starting with a nucleophile, and we're reacting it with our substrate. And so remember, our substrate is made of 2 parts, the carbon portion and a leaving group. So our bromine in this case is our leaving group. The red arrows are showing us the mechanism. So in our first arrow right here, we're going from the electrons on our nucleophile to the carbon that's attached to the leaving group. And remember that carbon's going to be partially positive because of that halogen, which means it's going to be an electrophile. So this is a nucleophilic attack followed by loss of a leaving group. So because our carbon can't have 5 bonds, these are happening at the same time. Nucleophilic attack is forming this new bond between the carbon and the oxygen, and as we have the bond move onto our bromine, onto our leaving group, we create this bromide anion here. So 2 things at a time: nucleophilic attack, loss of a leaving group. The transition state is shown down here. So remember, our transition state is the top of the hill, the top of our activation energy, but it's also kind of that halfway point. So the bond between the carbon and the oxygen is halfway formed, and the bond between the carbon and the bromine is halfway broken. This mechanism is referred to as a backside attack, and we call it that because our nucleophile is going to attack our carbon or bond to our carbon on the opposite side from that bromine. Because it's happening in this way, it's causing what we call inverted stereochemistry, and I'll have a little bit more on that in a couple slides. But it's really causing the substituents that are attached to that carbon to flip in another direction. I often like to think of it as an umbrella flipping inside out. So as we go through this, I'm going to create a summary list. So the first thing I'm going to put on my summary is the reaction / mechanism. So I'm going to write these out very generically, but we're going to start with our nucleophile, and we're going to react it with our substrate that has a leaving group attached to it. And we're going to go from that nucleophile to the carbon, and then to the leaving group. And so we will have our nucleophile bonded to our CH2 and our leaving group off on the side. So right now, that's the most important thing we know about it. A nucleophile is replacing that leaving group. So we're going to add to this list to talk about the rate of reaction. And we don't talk about rate of reactions or the speed of reactions very often because we aren't doing the math associated with it, and we're still not doing the math here, but we do need to understand the concepts. So here's our rate law. The rate is equal to K, our rate constant, times the concentration of the alkyl halide times the constant of the nucleophile. So this is a second order reaction because we have two compounds that are influencing how fast the reaction will go. So that means that if we change the concentration of either of these, it will affect the rate. This reaction rate is based off of RDS, the rate determining step. And because both of our molecules, our substrate and our nucleophile, are involved in the only step of the reaction, they're both included in that rate law. So I'm going to add this to my summary list. Ooh, discovering I have some dead markers here. Is our rate law. And so my rate law, rate equals K, substrate, nucleophile. I'm going to do a practice problem with this as well. So I'll bring this back and we'll add to it as we go through the chapter. But we're going to do a little practice problem to make sure that we understand how this affects our reaction. So if we have this reaction, we know that our rate law is K. This is a 1 propane. Reacting it with hydroxide. So we're going to look at two different questions or two different changes that could occur in this. So the first one is, what will happen to the rate if we double the concentration of our substrate? So if the concentration of our 1-bromopropane is doubled, what will happen to the rate? Because these are both first order with respect to equal, the change in rate is going to be directly proportional to the change in the concentration. So in this scenario, the rate will double, meaning it will go twice as fast. What if we cut the concentration of hydroxide by a third? So it's as 1/3 of as concentrated. How will that affect the rate? And the approach is the same. It's going to have a direct relationship. So the rate will be 1/3 as fast. It's going to go much slower. It's going to go 1/3 of the speed as it's going before. So there's a nice direct relationship between those concentrations and the speed of our reaction. So here's a little, let's move this guy. Here's a little GIF showing that inverted stereochemistry. So that's what we're going to focus on this slide, and then we're going to do a couple practice problems with it. There we go. So as I mentioned on our first slide, the stereochemistry of our product is going inverted compared to the stereochemistry of our reactant. Now, only relevant and only happens if there's a center where that leaving group was attached. So in our reaction, we have R2-bromobutane. So notice that is attached with a wedge. Our bromine is our leaving group. Nucleophile, our hydroxide, attacks our carbon. Let me draw in our reaction arrows here. So we're going to go from that oxygen to our carbon. That's our nucleophilic attack arrow. And then we're going to go from that bond onto that bromine. That's the of our leaving group. We're going to end up with a product where the alcohol is on the opposite side. So we're ending up with the mirror image of what we started. So in this case, S2-butanol. And then we have our bromine leaving group off on the side. It's showing us the same thing, but kind of in a cartoon version. So here's our file attacking our carbon. This orange one is our leaving group. In the middle here is our transition state. So we can see that the other substituents coming off that carbon go from pointing away from that leaving group to being planar, to being flat, and then end up pointing away from our new nucleophile that is bonded. And then up here in our little GIF, we can see the same idea as the other substituents move away. So the red is our nucleophile, there's our nucleophilic attack, the green leaving group, leaving the rest of that molecule. So let's do a couple practice problems to see how we do a problem. So I'm going to draw out two reactions. Now these are both SN2 reactions. And I'm specifically telling us that because later on we will have to make the decision as to what type of reaction our substituents are going through, but right now we only know one reaction, so we won't have any decisions to make. When we look at what we have our substrate, we have our leaving group, and we're reacting it with a SH attached to a sodium. So again, sodium, we can think of this as an negative charge. So we're going to nucleophilic attack onto our carbon, leaving group going to leave. So I know that I have a bromine kind of hanging out over here on the side. This carbon right here is going to that sulfur, but specifically because this is an SN2 reaction, chemistry needs to be inverted, it will be bonded in a wedged formation. So that bromine was coming out at the page at us, which means our sulfur attacks the back side, and so now our sulfur is going back into the page. Same idea on our second one. The entire structure here is our substrate. We have a chlorine leaving group. We're ignoring that counter ion, or that spectrum ion, and we have a hydroxide ion. So again, we're going to do that nucleophilic attack. The rest of the molecule stays in place. So we can draw the rest, figure out what's going on. There's our hydroxide attached in a dashed position that will have that inverted stereochemistry compared to the reactant. As we talk about these reactions in this chapter, we want to talk about all of the different pieces. So we've talked about the general mechanism and reaction, we've talked about the rate of the reaction, we've talked about the inverted stereochemistry. So we also need to talk about the substrate and the nucleophile. And so that's where our next couple slides are taking us. When we talk about the substrate in this chapter, we're looking at how sterically hindered it is. So we're comparing different reactants, and we have, and specifically for this column, we're looking at that alpha carbon, right where that leaving group is attached. We have a methyl group, a primary group, a secondary, and a tertiary. And this is showing us how fast these reactions are happening. So our relative rate right here is 145. This one is 1. So really we're setting the primary at 1. That means the methyl is 145 times faster. A secondary is 0.008, and then the tertiary is negligible, which means it just doesn't really happen. The reason why we have such a difference in speed is because our nucleophile is going to attack our carbon while our leaving group is still attached. If there's other things in the way of that backside attack, it's going to make the reaction either very slow or not even happen. Now, it's not just the alpha carbon that can affect this. The substituents on the beta carbon can have an effect as well. So here's our beta carbon that isn't bonded to anything other than our alpha carbon, a beta carbon with 1 substituent, with 2 substituents, and 3 substituents. And we can notice that with 0 or 1 substituents, it's about the same speed. And then as we go down to 2 substituents and 3 substituents, the speed of our reaction decreases quite a bit. So this tells us that our reaction is very sensitive to steric hindrance. So we're going to add this to our summary list. And I'm going to add our stereochemistry information to our summary list as well. Number 3 that I'm going to put here is that we end up with inverted stereochemistry. So we start with a wedge on our leaving group. We end up with a dash on our leaving group. Number 4 is our information. And how I'm going to summarize that, I'm going to say that a methyl is faster than a primary, faster than a secondary, which is faster than a tertiary. And really, with a tertiary, there is no reaction. And this is true for the alpha and the beta carbons. So we've got the general reaction. We've talked about the stereochemistry of our product versus our reagent. Oh, there's one more word I need to add in here. Let me find a pen that's a little skinnier. When we talk about that stereochemistry, the word that we use to describe it is that we say that it is specific. And stereospecific means that the stereos depend on the stereochemistry of the reactant. So I just wanted to move. All right, and then the last thing on my summary sheet here is our substrate, but we are going to add 2 more pieces of information to that as we finish up our last couple slides. So our next slide is talking about the nucleophile. And when we are doing a SN2 reaction, it is best to have a strong nucleophile. And we say that a nucleophile is strong based off of its charge and polarizability. The charge means, of course, that it's charged. So notice that our list of strong nucleophiles down here, everything has a negative charge. Polarizability, this is a word you learned back in general chemistry. Something is more polarizable if we can more easily move its electrons around. And so really that just means something that's larger. So sulfur is in the 3rd row of the periodic table and oxygen is in the 2nd row. So because sulfur is larger than oxygen, it's more polarizable, which means it's a stronger nucleophile than oxygen. Over in our weak nucleophile category are neutral compounds. So for our SN2, we know that we want to have a strong nucleophile. Number 5 here is that we want to have a nucleophile that is strong, which for the most part means that we want to have a negative charge. All right, last thing we need to talk about in regards to this reaction is the solvent. And before we can talk about the solvent that we want for the SN2 reaction, we need to talk about solvent categories in general. And so we can divide our solvents into 2 main categories. We can either classify them as polar or nonpolar. And our SN2 reaction does need to have a polar, but our polar solvents can also be divided up. And we can divide them into protic solvents and aprotic solvents. Protic solvents have hydrogens that are capable of hydrogen bonding. And so that means that they can hydrogen bond with our reagents. And polar aprotic solvents do not have any hydrogens available for hydrogen bonding. So our big difference here is that protic solvents can help stabilize cations and anions. The cations are stabilized because they have these electronegative atoms, oxygens, nitrogens, and the ions are stabilized because of those available hydrogens. In an aprotic solvent, the solvent can help stabilize cations, but not anions. So our negatively charged or partially negatively charged oxygens and nitrogens can surround a cation, but there isn't anything available to surround that anion. So in our SN2 reaction, we want to use a polar aprotic solvent. And our reasoning for that is because it doesn't stabilize anions. Our nucleophile is going to be an anion, and we don't want it to be stabilized. We want it to be reactive. If it's stabilized by the solvent, that's going to make it less reactive. So with a polar aprotic solvent, it starts our reaction off at a higher energy level, which means our activation energy, our hill, is a lot smaller. If we started with a protic solvent, the protic solvent would stabilize that nucleophile, making it harder for it to react. So for our SN2 reaction, we want to have polar aprotic solvent. So I'm going to add that last piece of it in here to list. So number 6 down here is solvent. And we're going to say that we want a polar aprotic solvent. And our last slide in this chapter then is essentially what I've been putting onto our clipboard down there. It's the summary of all of our information. So we have a good generic reaction here. We have our nucleophilic attack. We have our loss of our leaving group. We have our transition state showing the half formed and half broken bonds between our carbon and our oxygen nucleophile and our bromine leaving group. And then this is also showing that inverted stereochemistry. We have the rate of our reaction showing that it is second order overall. We know that our stereochemistry is inverted and stereospecific. We have our reaction rates based off of that substrate. So methyl is the fastest, tertiary is the slowest. So it slows down as it gets bulkier or as it has more steric hindrance. We know that we want to have a strong nucleophile, which means it should have a negative charge. And we know that we should be using a polar aprotic solvent. All right, that is it for our SN2 reaction. Thank you.